Hi friends, welcome to ACE Engineering Academy Deep Learn program. Those who are preparing for GATE examination. In engineering hydrology, for a brief discussion we take the chapter precipitation. Under the heading of the precipitation chapter, three major subtopics are important for GATE point of view. Very interestingly, all the three subtopics are important. Let us see what are they, what points must be known by you, and what type of numericals will be generally asked in the examination. First one is estimation of minimum number of rain gauge stations and optimum number of rain gauge stations. In this area, generally, question will be framed. Second most important one, he will ask about interpretation of missing rainfall data is also important. And the third subtopic, frequency distribution is also frequency distribution of a point rainfall. Let us see what type of things we should learn regarding these three topics. We'll see in detail. First one is in a given catchment area, minimum number of rain gauge stations. Generally, we follow IS code recommendations. Even though World's Meteorological Organization recommendations are also there, for Indian scenario, we follow IS code provisions. In plain area, one rain gauge station for every 520 square kilometers. In uneven surfaces, slightly elevated places, one rain gauge station for every 260 square kilometers. In hilly areas, one rain gauge station for every 130 square kilometers. Generally, we know more number of rain gauge stations are to be provided in the hilly area as compared to plain area. More number of rain gauge stations must be provided in the hilly area compared to plain area. Generally, we have to provide more number of rain gauge stations because of difference of the elevations. Variation of the rainfall is also very high. That's why we must provide the rain gauge stations in as much closer distances as possible. Even though these are the minimum number of rain gauge stations, with the help of the rainfall data of the existing rain gauge stations, we can fix up what is the optimum number of rain gauge stations. That area is commonly touched. We will see the optimum number of rain gauge stations in a given catchment if there is a catchment area, let us say, n number of stations are already existing. We got the rainfall data, n number of stations are there. We got the rainfall data, P1, P2, P3, P4, in the form of annual rainfalls, mean annual rainfalls we consider. Once we get the rainfall data, we calculate P bar, sum of the rainfalls of existing number of rain gauge stations divided by number of rain gauge stations will give the average depth of rainfall. Then we calculate standard deviation of the rainfall data. Standard deviation of the rainfall data, sigma is equal to square root of Pi minus P bar whole square by n minus 1. N is the number of rain gauge stations already existing. P1, P2, P3 are the mean annual rainfalls of respective rain gauge stations. P bar, just now we have calculated the average of the annual rainfalls. Then sigma value is the standard deviation. With the help of the arithmetic mean and standard deviation, we can calculate coefficient of variation. Coefficient of variation is given by, it is expressed in percentages, 100 into sigma divided by P bar. Coefficient of variation is coming from the rainfall data of already existing rain gauge stations, which is nothing but minimum number of rain gauge stations. Then if epsilon is the acceptable error or permissible error in the measurement of the rainfall data, epsilon % is the permissible error in the measurement of rainfall data, I can get optimum number of rain gauge stations is equal to CV by epsilon whole square. How many number of stations rainfall data, small n number of stations rainfall data is considered, capital N value you are able to deduce. If n is more than n, remaining stations we have to install now, satisfying all the conditions necessary for rain gauge stations. So you can, this formula is also giving you, if n is given by CV by epsilon whole square, is one important formula. If epsilon is lesser and lesser, n value increases enormously. There is also one important observation. If you want, if the error is minimized, least possible error if you consider, n value tends to infinity, as epsilon tends to 0%, n value tends to infinity, infinite number of rain gauge stations. Sometimes problems like, for example, coefficient of variation is 30% instead of 5% permissible error. if we accept up to 6% error, how many number of rain gauge stations cost is saved? Such type of questions are commonly asked. Simple formula, n is equal CV by epsilon whole square. You are able to calculate n1 CV by epsilon 1 whole square. With the initial error acceptable, you will get 36. N2 CV by epsilon 2 whole square, 30 by 6 whole square, you will get 25. With the 5% error, we have to provide 36 rain gauge stations. With the 6% error, by increasing 1% error extra, your number of rain gauge stations to be provided is 25. 36 has come down to 25. The cost of 11 rain gauge stations has been saved. That's what has asked the question. Whatever is the initial number of rain gauge stations is immaterial. Instead of 36, you have to provide 25 only. Cost of 11 rain gauge stations is saved. Such questions may appear. You may give directly some rainfall data of 3-4 stations. IS code recommended error is 10%. That also one point you can understand. So in this area, generally, calculation of arithmetic mean, calculation of the standard deviation, with the help of the rainfall data of the existing rain gauge stations, calculate coefficient of variation, and once we know the acceptable error epsilon, CV by epsilon whole square, you are able to get the type of problems very easily solved. Second area where question commonly asked is interpretation of the missing rainfall data. It is also, I feel, very important for GATE, especially for GATE 23. We may expect a question on this. Interpretation of missing rainfall data. All the three methods are important. Let us have a brief look at these three methods. Interpretation of the missing rainfall data. Three methods are available. Arithmetic mean method. The second method in the interpretation of missing rainfall data is the normal ratio method. And inverse square distance method. These three methods, all the three methods are equally important for our GATE preparation. In what situation, what method is adopted, we will see. There is a catchment area. Say some 4 rain gauge stations are there. To have the brief review of the three methods, 4 rain gauge stations are there, say 1, 2, 3, 4. Normal annual rainfalls N1, N2, N3, N4 are there. They are nothing but the average of the 35 years of yearly rainfall data is considered. For every station, we calculate the normal annual rainfall values, and then in the month of, let us say, August 2022, for 10 days time, 3 stations are operative. 3 stations are operative fourth station is found inoperative, let us imagine. For 10 days in the month of August 2022, say here the rainfall recorded is P1, here the rainfall recorded is P2, here the rainfall recorded is P3. I don't know what is the rainfall recorded. This particular rain gauge station has gone out of order because of some technical or non-technical problems. With your mathematical skills and genuinity, you should be in a position to interpret what might be the most probable value of the rainfall data recorded by the fourth rain gauge station in that particular time, during the which the other three rain gauge stations have recorded P1, P2, P3. 7 data is available, P1, P2, P3, P4 is missing, N1, N2, N3, N4 are there. How do you get? The option is, first you have to choose which one we should go. Shall we go for arithmetic mean method or normal ratio method? Which one is having the missing rainfall data? N4. Take closer margin of N4 plus or minus 10% of N4. If all the operative rain gauge stations N values, N1, N2, N3, all will belong to this category, go to arithmetic mean method. At least anyone does not belong to this, N4 plus or minus 10% of N4. If out of N1, N2, N3, at least one rain gauge station's normal annual rainfall is not falling in the 10% margin of N4, then I can say that they are not homologous, they are not belonging to the same category. When they do not belong to the same category, the only method option is the normal ratio method. When all the four are having the close margin of 10%, arithmetic mean method, otherwise normal ratio method. When n values are not available or otherwise, when you want to have the highest accuracy of the interpretation of the missing rainfall data, even though the method is laborious, tiresome, but most accurate value we can get by third method, that also we'll see. So for this we follow arithmetic mean method, for this we follow normal ratio method. In arithmetic mean method, P4 is missing because all are in the closed region. So simply P1 plus P2 plus P3 divided by 3. Missing rainfall data is equal arithmetic mean of rainfalls recorded in that particular reference time of all operative rain gauge stations. If out of n number of stations, only one station is inoperative, simply sum of the remaining n-1 number of rainfalls divided by n-1 will give the missing rainfall data. This formula is applicable when n1, n2, n3 fall within the 10% margin of n4, that is 1.1 to 0.9 times n4 or 0.9 to 1.1 times n4. In that range, if all of them are falling, go for the simplest method. In that missing time, whatever is the rainfalls recorded by the remaining three operative rain gauge stations, get their average, you are going to get the missing rainfall data. By chance, if N1 or N2 or N3 does not belong to N4 plus or minus 10% of N4, then normal ratio method by normal ratio method, normal ratio of the fourth station is equal arithmetic mean of remaining 3 operative rain gauge stations. We know P1, P2, P3. We know N1, N2, N3, N4. P4 value can easily be obtained from this. This formula is also very, very important. In 3-4 times in different competitive examinations of different standards, questions have appeared in this particular subtopic. And the principle is also very easy. When n values are in the closed region, you can just, if you suppose N1, N2, N3, N4 fall in the same closed group, you can just strike off them. What is P4? 1/3 of P1 plus P2 plus P3. That's what the formula we get. So both the formulas will give the concurrent value provided N1, N2, N3 are very, very close to N4. To say to what extent closeness can be defined, we say within the 10% margin of normal annual rainfall of inoperative rain gauge station. That's how we take up to give a mathematical definition or mathematical validity. We take the 10% as the acceptable error, 10% that way, this way, 0.9 to 1.1 times N4. Within that margin, if all the N values fall, go for arithmetic mean method. Take the rain gauge stations belonging to same group, otherwise diversified group. Then you have to go for simple principle. Normal ratio of the inoperative rain gauge station is equal to arithmetic mean of normal ratios of all operative rain gauge stations. If you take the simple example, 3 rain gauge stations are there. Normal annual rainfall 120 centimeter, 110 centimeter, 125 centimeters. In 1 week during the month of July or September, August, here rainfall 6 centimeter, here rainfall 7 centimeter, here missing. A problem is given, let us say, in the first week of February 2023. 3 rain gauge stations, 2 rainfalls are given. 3rd rainfall के बारे में हमको जानकारी करना चाहिए. How do you get the missing rainfall data? Check. 125 is the n value. Plus or minus 10% is 12.5. 125 plus or minus 12.5. 112.5 to 137.5. This 110 is outside the range. That no other option, you have to go for normal ratio method. So P3 divided by 125, remaining only 2 half of. P1 6 divided by 120, 7 divided by, say this is 110, okay, 7 by 110, simplify, you can get the value. P3 value can be estimated very easily. These type of problems are also likely to come in your GATE preparation. Please understand. Let us see the third method, inverse square distance method. In what situations this ISD method is preferred to interpret the missing rainfall data? Number 1, when n values are not available, or otherwise when highest accuracy is needed. Highest accuracy in the interpretation of the missing rainfall data is needed. In any one of these situations, we have to go for adaptation of inverse square distance method for the purpose of interpretation of the missing rainfall data. What is the principle involved? Please see, in this method, there is a catchment area. Say here 2 rain gauge stations are there. Here rainfall is 6 centimeter. Here rainfall is 8 centimeter. 3rd station is having the missing rainfall data. then what is this principle involved? Here n values are not available. We will see this is at a distance of R1, it is at a distance of R2. We will trace the rain gauge stations. The actual distance between the rain gauge stations is to be measured physically. R1, R2 values are known to you. Then your P3 can be P1 by R1 square plus P2 by R2 square divided by 1 by R1 square plus 1 by R2 square. This formula will give you any rainfall in the closer distance the surrounding rain gauge station also will get almost the nearer value of the rainfall. If the rain gauge station is closer, suppose if R1 is 100 kilometer, R2 is some 300 kilometer, your answer P3 will be closer to 6. The simple formula we get, imagine this is 50 kilometers, say this is 100 kilometers distance. I can get the answer very easily. 6 divided by 50 square, 8 divided by 100 square divided by 1 by 50 square plus 1 by 100 square. Straight away you will get the value very easily. We can get it. This is 1 by 50 square common, 6 plus 8 by 4, 1 plus 1 by 4. If you take 1 by 50 square common in both numerator and denominator, within fraction of seconds you can get the problem solved. 6 plus 2, 8 divided by 5 by 4, 32 by 5, you will get 6.4 centimeter. Will be the missing rainfall data. Will be the missing rainfall data. Here how much value you are able to get? 6 point, because it is a 50 kilometers distance, because it is nearer, the missing rainfall data will be closer to the rainfall value between which whenever there is a closer distance, rainfalls are nearer. See 6 and 8, it is 50 kilometer, 100 kilometer, so it is closer to 6 centimeter. Answer for the problem is 6.4 centimeter. You may ask, in which of the following situations arithmetic mean method, ISD method will give the same missing rainfall value? If R1 is equal to R2, P1 plus P2 by R square, 1 plus 1 by R square, 2 by R square, R square gets cancelled, P1 plus P2 by 2. So, in which case first method and third method will give same missing rainfall data value when all operative rain gauge stations are equidistant from the inoperative rain gauge station, you get the same data, same missing rainfall value. You may ask, in which of the following situations arithmetic mean method and normal ratio method will give the same interpreted missing rainfall data value when n values are in the closed group? N value within the 10% margin of N4 inoperative stations n value, in that range, if all other n values are falling, you can say they belong to the same group. Cancellation of n, the first method and second method will give the same missing rainfall value. This area also, I feel, in the chapter of precipitation, equally important is arithmetic calculation of the average depth of rainfall. We discussed in some other classes. Arithmetic mean method, Thesian polygon method and isohydral method. This is also an important area. I feel this time a question may be expected from either in the region of optimum number of rain gauge stations and the excess number of rain gauge stations to be installed, and also interpretation of the missing rainfall data is also one of the expected areas as far as my perception is concerned. One more important topic in the chapter of precipitation, what I feel, is about the frequency distribution of the rainfall. About the frequency distribution of the rainfall. One more most expected topic, most expected question from my point of view, frequency distribution of point rainfall. Rainfall recorded by a particular rain gauge station is called point rainfall. We know the purpose of the chapter. With the help of the past rainfall data, with the help of past rainfall data, with the help of the past rainfall data, statistical or rational guess, statistical guess about future rainfall data. That is the purpose of the topic. Future rainfall data. You got the rainfall data of some number of years. With the help of that rainfall data of the previous years, you are able to guess about the future rainfall. That's what we are going to see in the frequency distribution of rainfall. In this particular theory, first step is always to calculate return period is the most important parameter, mostly wanted parameter. What is the return period or recurrence period? It is the minimum time taken for the reoccurrence of the rainfall equaling or exceeding at a particular rain gauge station for the particular duration of the reference rainfall. Within what minimum time a particular rainfall is getting equaled or exceeded, that is called return period. We got say some 10 years of rainfall data is available to you for a particular rain gauge station, station X, say station X in Bengaluru. A rain gauge station X is taken as a reference. From that rain gauge station, 10 years of previous rainfall data is available. Write them in the descending order. Go on giving the order, highest rainfall rank 1 up to 10. Whatever is the reference rainfall given to us, observe what is the rank. The return period is given by n plus 1 by m. By default, we use Weibel's formula. Even though other formulas are available, the other formulas are to be adopted, only they are mentioned like that. Otherwise, you need not think of the California's formula, Hazen-Williams formula, Colebrook or not Colebrook formula. The other formulas also. Weibel's formula is the formula we have to use by default to calculate the return period. N is the number of years of past rainfall data available. Past rainfall data, how long? कितने सालों से हमारे पास a particular rain gauge station का rainfall मौजूद, that is n. When you write all the n number of years of rainfall data with highest rainfall rank 1, least rainfall of all the previous n years data ranked n, last least rainfall ranked n, highest rainfall rank 1, then whatever reference rainfall is given, whose return period is needed. For that, I will identify in that list where is that rank. Formula is very simple. T is equal to n plus 1 divided by m. Once you calculate the return period, you can calculate probability of exceedance. What do you mean by probability of exceedance? Chance exceedance. P is the symbol, it is the reciprocal of return period. What is meant by probability of exceedance? Chances of, fractional chance or percentage chance of getting a rainfall equal to or exceeding in the next year. Probability of getting a particular rainfall equaling or exceeding in the coming year, the chances of occurrence is P. Chances of non-occurrence is Q. Probability of non-exceedance Q, that is 1 minus P, 1 minus 1 divided by T. I know the probability of occurring of a particular rainfall in the next year. What are the chances of not getting the rainfall in the coming year? If 20% chances are occurrence, 80% chances are non-occurrence, So P plus Q is always 1 by when you take fraction wise, percentage wise P plus Q is 100%. In this mathematical formulae, advisable to take only in fractions. Only in fractions. P, probability of exceedance, chances of reoccurrence of a particular rainfall at that rain gauge station in the coming year, which is nothing but reciprocal of return period. Non-occurrence, 1 minus P. 1 minus chances of exceedance. 1 minus probability of exceedance is equal to probability of non-exceedance. Ek bar, to occur, not to occur, chances are known. Now study, guess about the future rainfall data of the coming n years. Now, in coming n years, आने वाले भविष्य क्या, in the coming n years, what are the chances of getting that particular rainfall, some rainfall X? What are the chances of getting the rainfall means equaling or exceeding that rainfall? Exactly R times. Exactly R times in coming n years. Binomial distribution, general term. I want X times, exactly R times. Success must be exactly R times. Your formula, NCR, P power R, Q power N minus R. Don't forget, Q is nothing but 1 minus P. If P is 0.36, Q will be 0.64. P is known, Q can be computed, Q is known, P is known already. N, out of N coming years, we are guessing. R, how many number of times you want to get that particular rainfall equaled or exceeded. You can get this, a very wonderful formula. It's the general term in the expansion of P plus Q to the power of N. General term of the binomial expansion we are able to get. This is the first useful formula in the chapter. Second useful formula, at least R number of times. At least R times in the coming n years. In the coming n years, dear friends, very easily we can get. I want at least R times equal to R or more than R number of years. Summation NCR P power R Q power N minus R R value starts from R to N. NCR, P power R, Q power N minus R, sum up, summation function, R value starts from R to N, you are going to get. For example, at least 6 times in the coming 10 years. At least 6 times a particular expected rainfall should occur in the coming 10 years. At least 6 times means, at least means 6, 7, 8, 9, 10. 10C6, P power 6, Q power 4 plus 10C7, P power 7, Q power 3 plus 10C8, P power 8, Q power 2 plus 10C9, P power 9, Q power 1 plus 10C10, P power 10, Q power 0. That much lengthy problem may not be given in GATE examination. Simply, you may ask in the multiple choice summation function like this. This is also one important expected area for the coming GATE examination. Pyare dost. If you see the case number 3, my dear friends, not even once, what is the chances of not getting the rainfall at least once in the coming n years? Every time that your rainfall, expected rainfall is not going to occur. All the coming n years you are going to fail in guessing about the rainfall data, about the expected rainfall. Yani P of x is equal 0. Number of occurrences are 0 because has asked what are the chances of getting that particular rainfall at that particular rain gauge station. Not even once in the coming 4 years. Not even once in the coming 20 years. Simply put, R is equal to 0. What is meant by R? The number of successes you want in the coming n years. Getting? So please, simply NC0, P power 0, Q power n minus 0, NC0 is 1, P power 0 is 1, Q power n. Simple formula. What is the probability of getting a particular rainfall at a particular rain gauge station for that particular duration? Not even once in the coming n years. Simple. Every time it's a failure for the coming n years. This year, coming year, the next coming year, Q like that. For all the coming n years, conditional probability, Q power n is the required chances of not getting the rainfall at least once, not even once in the coming n years. And the most important of this subtopic, which I feel at least once, what are the chances of getting a particular rainfall at a particular rain gauge station with a particular duration? What are the chances of occurrence of that particular rainfall at least once in the coming n years? This is not even once, it is at least once. Not even once and at least once are complementary. Probability of x is equal to 0. Probability of x greater than 0. This is not even once. This is at least once. Sum of these two probabilities is 1. I want probability of x greater than 0 means at least once. 1 minus probability of x is equal to 0. This is a very important formula of the entire subtopic. What is the chances of getting a particular rainfall at a particular rain gauge station at least once in the coming 6 years? 1 minus q power 6. In the coming 4 years, 1 minus q power 4. Q, 1 minus P, 1 by return period. From what data return period is expected? From the previous rainfall data. From the previous rainfall data, return period is calculated. Return period. With the help of the data already available, from the data of the rainfall data of the particular rain gauge station, we calculate the return period. Return period is obtained by experience of the particular, what is the experience felt by that particular rain gauge station, what are the previous years of rainfall data recorded. That's why, dear friends, guessing about the future rainfall data on the basis of previous rainfall data. Previous rainfall data will give the return period T. T will give the values of P and Q. With the help of P and Q, everywhere with the help of P and Q, in the coming n years, to get R number of times or at least R number of times like that, we are able to get this type of problems likely to come in the GATE examination in my aspect of view. Let us see. Suppose if a question is given, a particular rainfall is expected, a particular rainfall of return period 100 years, or say is expected at least once in the coming 3 years, or say this is 10 years. Return period, chances of occurrence is once in 10 years at least. What is the probability of getting the rainfall at least once in the coming 3 years? Direct, at least once. Not even once in the coming 3 years, q power 3. At least once, 1 minus q power 3 is the answer. But you should get q. What is the return period T? T is 10 years, so P is 1 by 10. So q will be 1 minus P, that is 1 minus 0.1, 0.9. 1 minus 0.9 to the power of 3. 0.9 into 0.9, 0.81 into 9, 0.9, 0.729, 1 minus 0.729, you will get 0.271. So percentage wise, if for a particular rainfall, if the return period at a particular rain gauge station is 10 years, at that station, what are the chances of getting the rainfall at that particular rainfall for which the return period is 10 years? Expected at least once in the coming 3 years. 27.1% chances are there. At least, not even once in the coming 3 years. 0.9 to the power of 3, 0.729 is the answer. At least twice in the coming 3 years. At least twice. At least twice in the coming 3 years. At least twice in the coming, at least twice. Probability of greater than or equal to 2, at least twice. That is probability of 2 number of times, probability of 3 number of times. Out of coming 3 years, 2 times. 3C2, P power 2, Q power 1, and all the 3 years. At least 2 times in the coming 3 years implies every time the rainfall is going to be equaling or exceeding that particular rainfall. Every year is a success, simply P power 3. 3C2 is 3. P square 0.9 to the power of P is 0.1. P square is 0.01 into 0.9, 0.1 whole cube. You can simplify 0.009 into 3, 0.027 plus 0.10 to the power of minus 3, 0.001, you will get 0.028. That's how you are going to get multiply with 100, 2.8% chances you are able to get. So this way of solving the problems, we can probability of getting x value more than 2, equaling and more than 2, 2 times and 3 times. 2 times, 3 times, sum up, you are going to get this value in percentages. Here, at least once in the coming 3 years, definitely this value is higher. Out of the coming 3 years, at least once chances. Here, at least twice in the coming 3 years. If possible, all the 3 years, otherwise at least 2 times. 2 times and 3 times. Your chances are going to get reduced. There, 27%, here only 2.8%. So, with reference to the precipitation chapter, I feel these are the important areas and important concepts. Don't neglect calculation of average rainfall also. Other topics we explained already. Regarding this precipitation, I guess it is 100% one question will come as per my guessing, and that too, minimum number of rain gauge stations, optimum number of rain gauge stations, next, interpretation of the missing rainfall data, next, frequency distribution of the point rainfall at a particular rain gauge station. That is my idea, my dear friends. I wish you all the best, good luck, and thanks once again for this deep learning program, ACE Engineering Academy.